A ball of mass m is attached to a string of length L. It is being swung in a vertical circle with enough speed that the spring remains taut throughout the ball's motion. Assume the ball travels freely in this vertical circle with negligible loss of total mechanical energy. At the top and bottom of the circle, the ball's speeds are Vt and Vb, and the corresponding tensions are Tt and Tb. Tt and Tb have magnitudes Tt and Tb. Find Tb minus T, the difference between the magnitude of tension and the strain at the bottom relative to the strain at the top. Alright, so let's talk about how to connect these to things. Let's say we have Vt at the top. We have Vb at the bottom. Of course, this distance is 2L. So, at the top, we have a free body diagram that looks like this. We have the weight pulling down. We have the tension pulling down. Let's use their notations. So that's the tension at the top. And of course we have an acceleration, which points to the center, which I'm going to call ACT for at the top. So we would have something along the lines of Ft plus m times g is m times Vt squared over L, because it's tracking out a circle of radius L. So this is the centripetal acceleration. Right. At the bottom of the arc, we have the weight pulling down, just like before. That happened. But now we have the tension pulling up, which they call FTB, and there is a centripetal acceleration upward, which is ACB. And so I have, you know what, I still use the wrong notation here. Let me fix this. That is the tension, but the tension that I wanted is tension at the top. And likewise down here, I'll have the tension at the bottom minus mg, and that'll be mvb squared over L. Seems like we don't have enough information, but we haven't done one last thing. Let's see if I can fit this over here. Oops. We haven't done energy balance. So the energy at the top equals the energy at the bottom. The energy at the top is mg times 2L plus the kinetic energy at the top, 1/2 mv top squared, relative to the bottom. And it should be the same amount, of course, but it will be 0 plus 1/2 mv bottom squared. And then probably the best way to go with this, which I think I'll do on the page, is to solve these squares and figure out what they should be. So let's see if we can pull that off. So let's see. Looking at the top guy, we would have something like mv top squared. So I'm going to look at this equation, and I'm going to end up with that equals tension at the top times L plus mgl. And likewise, looking at this one, we're going to get that mv bottom squared is tension at the bottom L minus mgl. something like that. So if we go over to the energy balance, we'll have 2 mgl. Let's give ourselves a little bit more room here, a little bit at least, plus 1/2 tension at the top plus mgl, and that will equal 1/2 tension at the bottom times L minus mgl, all in parentheses. Well, and I'm missing an L over here. Sorry, let me rewrite that. I'm going to come down here actually and rewrite it. So 2 mgl plus 1/2 T sub T L plus mgl equals 1/2 T sub B L minus mgl. And now it is really just kind of stupid algebra tricks, right? Here we have 2 mgl plus 1/2. Oh, actually, you know what? Before I even do that, let's just get rid of the L's. Cancel the L's entirely before we go any further. So 2 mg plus 1/2 T sub T plus 1/2 mg equals 1/2 TB minus 1/2 mg. Alrighty, so now I think I want to bring this guy over here, and I want to bring this one over here, leaving me with 2 mg plus 1/2 mg plus another 1/2 mg equals 1/2 TB minus 1/2 T sub T. Which of course is 1/2 TB minus TT, which is what we're looking for. So yay. We cross multiply by the 1/2. Over here, this whole thing is really 3. So I'll have 3 mg equals 1/2 of the difference that I'm looking for. So the difference that I'm looking for should be 6 mg. Can't really say that's anything deep, but you know, it is an answer. And Master Physics says it is the right answer, so yay. It's sort of interesting that it doesn't matter what the speeds are. As long as we can make it around, the difference is always going to be 6 times the weight. That's sort of interesting.